Hello, viewers. My name is Ryan Gear, and I am a Clemson University student studying to become a mechanical engineer. According to most of the world, mechanical engineering is one of the broadest types of engineering. Since it is broad, it is only fitting for mechanical engineering to have aspects of other types of engineering. And in this video, I will be discussing how material science will play an important role in my future profession in becoming a mechanical engineer. I have not given too much thought on what engineering company I would like to work for when I graduate, but I've always been fond of designing projects, whether it is for my company or something that could change the world for the better. I think one of my jobs will feature the strengthening of materials, which takes a microscopic approach. Most of the time, mechanical engineers work in the macroscopic world. Material science will assist me in fully understanding and completing the task. Material science is the study of relationships between processing, properties, and performance of materials that enables engineering function. A mechanical engineer may design a machine to perform a task, but the success of the machine is based on the material that is used. This is why mechanical engineers and material scientists must work together. The machine can be strengthened to complete a certain task by using the process of diffusion. A way to perform this task is by diffusion. Diffusion is the process at which atoms move into a material. Solute atoms are atoms with low concentration, while solvent atoms are atoms with high concentration. Atoms move either by vacancy or interstitial movement. During the process of vacancy diffusion, the bonds are broken and the atom goes into the vacant site. During the process of interstitial diffusion, the solute atoms fit into the interstitial sites. And yes, an atom can fit into the site due to the atomic packing factor being less than 1. The atomic packing factor is the ratio of the volume of the atom and the volume of the unit cell. If the APF is 1, then the atom fits perfectly in the unit cell. However, assuming that atoms are spheres and the unit cell is a cube, the APF will never be 1. Almost like putting oranges in a box. No matter how small or how many oranges are in the box will always have open space. But back to diffusion. There are two types of diffusion, steady state and non-steady state diffusion. Steady state means that there is no change with respect to time compared to non-steady state. Now let's do a problem. What is the diffusion coefficient D for the inner diffusion of carbon in alpha iron body-centered cubic at 800 degrees Celsius? This is the diffusion coefficient formula. Some of these terms are not defined, but we do know for the inner diffusion of carbon in alpha iron, which is a body-centered cubic crystal structure, we do have a table for that. And the table is as shown, table 5.2. My mistake, it's table 6.2. Carbon is the diffusing species and alpha iron is the host metal. The diffusion coefficient is as given. 7.87 times 10 to the negative 11 meters squared over seconds. Let's look at this one. You are working for Intech and your job is to harden titanium by the diffusion of carbon. The concentration of carbon at 2 millimeters into the surface of the titanium slab is 0.28 kilograms per meter cubed, and at 6 millimeters the concentration is 0.72 kilograms per meter cubed. The temperature of the carburizing environment is 897 degrees Celsius, and the rate at which carbon is entering this 3 millimeters thick region is 1.3 times e to the negative 9 kilograms meters per meters squared times second. What is the diffusion coefficient for this particular treatment? Using Fick's first law, we can assume that the diffusion flux and the concentration are in steady state. As stated in the problem statement, the change in length goes from 2 millimeters to 6 millimeters, and the concentration goes from 0.72 kilograms meters cubed to 0.28 kilograms meters cubed.
through calculator work, you should get this value. Since we are given the diffusion flux, and we solve for the change in concentration over the change in length, we can solve for the diffusion rate, which is 1.21 times 10 to the negative 11 meters squared over seconds. In conclusion, in order to become an effective mechanical engineer, I must be able to use other types of engineering, like material science, to accomplish the task. This not only applies to mechanical engineers, but all the types of engineering. This is just the tip of the iceberg. It may seem difficult to go out of my comfort zone and learn about other things of engineering, but to become a professional engineer, it must be done, and it will be done. The end.